Today we are completing the course with the last chapter on correlation and regression. So we are going to learn about correlation, regression. We will discuss about coefficient of determination and standard error of estimate. In this chapter, you will learn how to draw a scatter plot for a set of ordered pairs, compute the correlation coefficient, test the significance of a correlation coefficient, and compute the equation of the regression, the coefficient of determination and non-determination, and the standard error of estimate. We will also learn how to make prediction using an independent value. Correlation is a statistical study which consists of determining whether there is a relation between between a dependent variable y and one or more independent variable. If there is only one independent variable, we will call it a simple correlation. In case there are more than one independent variable, we call it a multiple correlation. A regression is a statistical study used to describe the nature of the relationship between the variables. So the main question we generally ask in correlation is whether or not there is a relation between one, two, or more variables. And if there is a relation, what is the strength of that relation? Also, we will want to know what is the type of relation. Is it linear or nonlinear? So there are generally two types of variables in correlation: independent variable and a dependent variable. There is generally one dependent variable and one or more independent variables. A scatter diagram is used to determine if there is a linear relationship or not between variables. It consists of plotting the values x and y on a rectangular coordinate system and then check if the plot reflects a linear or a nonlinear relationship. Let's use Excel to plot the values of this example. We want to construct a scatter plot for the data shown for rental car company in the United States for a recent year, to determine what is the type of relation between the number of cars in thousand and the revenue. The number of cars is in 10,000 and the revenue is in billions of dollars. So I'm going to type here the values of number of cars, and here, which is the independent variable. And then and y, which is the revenue. So here we have 63, 29, 20.8, 19.1, 13.4, 8.5. Here 7, 3.9, 2.1, 2.8, 1.4, 1.5. So we have two variables, x and y. What I do is I will highlight both variables and insert a scatter plot. This is the scatter plot here. And this is the plot representing the relation between the number of cars in 10 of thousands and the revenue of the company, Y. So with this, we can feel like this point could get close enough to a line. So the relationship could be called a linear relationship. The correlation coefficient is used to determine to measure the strength and the direction of a possible linear relation between two variables. A positive correlation is, if R is positive, the relation is positive. If R is negative, the relation is negative. A positive relationship means that it is an increasing relationship. That is, as X increases, Y increases, and vice versa. A negative relationship is a decreasing relation in which as X increases, Y decreases. So the correlation coefficient R is generally a value between -1 and 1. The stronger the relation is, the closer it will be to either -1 or 1. A perfect relationship is when R equals to either -1 or positive 1. So these are some examples of scatter diagram. The first three are positive relationship. The third one is a perfect linear relation. So the sixth one is a perfect negative relation. The correlation coefficient is obtained using the following formula. So let's use the example that we had to find the correlation coefficient of number of cars in 10,000s and the revenue in billions. So you can fit this formula into your calculator, but I will advise you to use Excel. So we are going to go back and learn how to use Excel to find this correlation coefficient. So to find the correlation coefficient, you go to Excel and choose data, then data analysis. We are going to look for regression. This is regression. And we are going to have the information that we need. The input R is what we put here as the dependent variable. The input Y is the dependent variable, and the input X is the independent variable. I will highlight A2 to A7. So we can choose to have, our graph. I will say, I will put it here in D3. And we press OK. So the correlation coefficient R is here. Multiple R is the correlation coefficient, which is 0.98. We will go back to the PowerPoint to compare our results with what is obtained from the formula. So you will see R is 0.982. which depict a strong positive relationship. So when r equals to 0, we will say there is no relationship between x and y. And when r is, the closer it is to r or -1, as I said before, there is a strong correlation between x and y. When we say there is a strong correlation, it does not mean there is a significant correlation. The test for significance is the hypothesis about the correlation coefficient rho. So the null hypothesis is that rho equals to 0, meaning there is no correlation between x and y. And the alternative hypothesis is rho is different from 0, rho is greater than 0, rho is less than 0, which is a form of r being different from 0, will mean there is a significant correlation between x and y. The test value for testing correlation coefficient is r, t equals to r times square root of n minus 2 over 1 minus r squared. We use the t distribution. When you are using the t distribution with the degree of freedom equals to n minus 2. We can always find this from Excel. We can use, if you learn how to use Excel, you will get the test value from Excel. If you are using the critical value as we did in chapter 8, you will have to go with the level of significance 0.05, degree of freedom 4. You want to find the test value. Using your textbook, from the table in your textbook, in page 652, the degree of freedom is 4. We are using a two-tailed test here. So the critical values are plus or minus 2.776. Alpha equals to 0.05, degree of freedom of 4. You have 2.776, which is the critical value. If you are using the t distribution, you fit in the values r, n minus n is 6, and r squared, you get a test value of 10.4, which is above 2.772, so it's in the rejection region. We reject the null hypothesis, and that means there is a significant correlation between x and y. Another method of testing is with the use of the PPMC table. The PPMC table is in your book as well. It's a much simpler table, or it uses a much easier test value. You can find it in page 659. 659. So using table I, which is in page 659, test the significance of the correlation coefficient R equals to 0.067 from example 10.3 in your textbook. So when you are using table I, which is the PPMC table, the test value is R, the correlation coefficient. So if you go to that table, you have two levels of significance, 0.05 and 0.01. And if you look at example 3 in your textbook, let's go to example 3, 10.3, example 3. This example is not example 3. Test of significance. Okay, this example in your textbook is example 10.6. We want to test the significance of R at alpha equal to 0.01 when R is 0.0442. So this is 0.0442. And this example is actually example 10.6. So to test for significance of correlation, H0 is rho equals to 0, H1 is rho is different from 0. The degree of freedom is 9 minus 2, which is 7. So looking at the table I, you will see that this table in page 656. With alpha equal to 0.01, degree of freedom of 7, you have 0.798 as the critical values. This table is good when alpha is equal to 0.05 or 0.01. You choose the test value to be R. You don't use the formula R times square root of n minus 2 over 1 minus R squared. In this type of situation, you use R equals to the test value is R. And then you compare it to these critical values that you read from table I. And since R is between negative 0.798 and 0.798, we do not reject the null hypothesis, so there is not enough evidence to say that there is a significant linear relationship between the variables. So there are several situations in which a relation could be between two variables. We have the direct cause and effect relationship between the variable, that is x causes y. We have the reverse cause and effect relationship, y causes x. We have the relationship between the variables may be caused by a third variable, and then there may be a complexity of interrelationship among many variables, or the relationship may just be coincidental. So it is not always because there is a statistical relationship that you will conclude that there is a relationship. Let's start with the first example. There is a relationship, there is a reverse cause and effect relationship between the variable. That is, for example, water causes plant to grow, poison causes death, heat causes ice to melt. These are direct cause and effect relationship. These are direct example of direct cause. Let's look at reverse relationship. Suppose a researcher believes excessive coffee consumption causes nervousness, but the researcher fails to consider that the reverse situation may occur. That is, it may be an extremely nervous person that craves for coffee to calm his nerves. So it's not the coffee that caused the nerve, it is the nerve that made the person to drink coffee. So the relationship between variables may be caused by a third variable. If a statistician correlated the number of deaths due to drowning and the number of cans of soft drink consumed daily during the summer, he or she would probably find a significant relationship. However, the soft drink is not necessarily responsible for the death, since both variables may be related to heat and humidity. So there is a third cause of the relation between the number of deaths due to drowning and the number of cans of soft drink consumed daily. A researcher may find a significant relationship between students' high school grade and college grade, but there probably are many other variables involved, such as IQ, hours of study, even the university where you go to, influence of parents' motivation. Here we have an example of a large complexity of interrelationship between the grade in high school and the grade in college. Also, the relationship may be coincidental. A researcher may be able to find a significant relationship between the increase in the number of people who are exercising and the increase in the number of people who are committing crimes. But common sense dictates that any relationship between these two values must be due to coincidence. So when we have a relationship between two variables, if there is a linear relationship, we may want to describe that relationship with a straight line. So the line that is the closest to all the points of a scatter plot is called the regression line. It is generally obtained with the equation that we have below, where y prime is the closest line to the point of the scatter plot, y prime equals to a plus bx. A is called the intercept, while b is called the slope. So we can generally obtain the formula for this line using Excel again. I will go back to Excel so that we see how to find the values A and B. You enter the values on Excel as we did for X and Y. And here we have this is the y-intercept 0.396 or 0.4. And this is the slope. So you enter your value to Excel and run the regression to get the intercept and the slope. So we have y prime equal to 0.396 plus 0.106x. So if in our example of car rental companies, we have y, and we can now make a prediction. Suppose we want to make a prediction for a value x equals to 15. We replace x into the equation, and then we find out that y prime equals to 1.96. So if we replace by 40, we will have y prime equal to 4.63. So you can make prediction by replacing the value of x in the equation of y prime. So we have our regression line here. For example, use the equation of the regression line to predict the income of a car rental agency that has 200,000 automobile. So for 200,000, since they are given in 10 of 1,000, x equals to 20. Always make sure you choose the right unit. And we replace into the equation to have y prime equal to 2.516 billion. So the magnitude of the change in one variable when the other variable changes exactly 1 unit is called the marginal change. The value of the slope b of the regression line equation represents that marginal change. For a valid prediction, the value of the correlation coefficient must be significant. That's what we do the test of significance. When R is not significantly different from 0, The best predictor of y is the mean of the data values of y. We call a prediction an extrapolation when the value we are using to make that prediction is out of the range of values of x. Otherwise, it is an interpolation. So in computing the variance of a variable, we usually first found the sum of the square of the deviations from the mean, which is called the total variation. If we have our regression line, y prime, the explained variation is y prime minus y bar. Y prime minus y bar is called the explained variation. In this explained variation, we use the prediction, the predicted values, together with the mean of the y. Now, the difference between the predicted value and the actual value y is called the residual. The sum of the square of the residual is called the explained variation. So the coefficient of determination is r squared, that is the square of r. It is the proportion of variation of the dependent variable that can be explained by the regression line and the independent variable. So if you are asked to find the coefficient of determination, just square r, but it is actually the fraction of the explained variable with respect to the total, the explained variation with respect to the total variation. And the coefficient of non-determination is 1 minus r squared. The standard error is the square root of the unexplained variation divided by the degree of freedom n minus 2. You can get the standard error also from Excel. Let me go back to the example we did before and look at the Excel output. In this, we have R equal to 0.982 is the correlation coefficient. When you square it, you get R squared, which is the coefficient of determination. The standard error is here, 0.447. So the standard error of estimate is generally used to compute the confidence interval for the prediction of a point y. You start with y prime, which is the point estimate of y obtained from prediction given the value of x. You replace it into the equation to get the confidence interval for y. This is just for your knowledge. I do not ask you to do this type of computation generally. So we are done at this point. So you should be able to, given data values, x and y, to make a scatter diagram using Excel, and to use Excel again to make an Excel output of the regression. It will provide you with the correlation coefficient. It will provide you with the intercept and the slope for the regression line. It will provide you with the coefficient of determination and non-determination. It will also provide you with the standard error of estimate. You will be able to use R as the test value and the table I, which is in your textbook with degree of freedom 2, to find the critical point and determine if R is in the rejection region, the correlation is significant. Otherwise, it is not a significant correlation. If you have any question, you can send me an email and make sure you do your homework and take the quizzes. If during the quiz you have questions, don't hesitate to contact me.